All right, friends, couple of good questions over the break that just wanted to mention briefly, and I've already forgotten some of them. There was a question about why potassium tertbutoxide is a sterically hindered base. And the issue is, I mean, if you just draw it in its skeletal figure, it looks like, oh, the oxygen's poking out there away from the methyl groups. No big deal. If you actually look at, yeah, that went very badly there. If you look at what tert butoxide actually looks like in a space-filling sense, um, ignore the proton that's there on that oxygen. This is tertiary butanol, the conjugate acid of T-butoxide, but I can't draw the negatively charged version in Spartan. So just imagine that that's a negatively charged oxygen. You can see that those methyl groups start to get in the way of that oxygen's ability to attack carbon. Okay? So this is a separate issue entirely. There was some confusion about how this is related to the substitution of the alkyl halide, whether it's primary, secondary, or tertiary. This is a separate issue entirely. This is about the ability of the nucleophile / base to approach the sp3 hybridized carbon in your alkyl halide. And no matter what that sp3 hybridized carbon in your alkyl halide is, these methyl groups on T-butoxide are going to interfere with its ability to attack the carbon. And so all that's left is to be able to remove protons. So I would put T-butoxide in a list of molecules that you memorize that are just too bulky to attack carbon and instead will attack hydrogen. Not good nucleophiles, but are good bases. Let's see, and then... and then there was a question about some things that you may have found in the reading. The Smith text talks a little bit about solvents for these reactions and mentions the difference between protic solvent and aprotic solvent. It also talks about the difference between polar solvent and nonpolar solvent. Both protic and aprotic solvents, polar solvents are those that have polar bonds where there's an electronegative atom attached to a less electronegative atom, so there's a dipole. Nonpolar solvents are like hexanes, hexane or benzene, things that don't have electronegative or don't have permanent dipoles. Protic solvents are those that have, if Z is an electronegative atom, ZH sigma bonds. So these are solvents that can be hydrogen bond donors, and they can also be acids. Aprotic solvents are solvents that don't have electronegative bonds between hydrogen and an electronegative atom. So these are not hydrogen bond donors. This distinction is not that important. I frankly it is important from a practical point of view, though I'm not going to ask you which of the following is a polar aprotic solvent or whatnot, just because I have bigger fish to fry than that. The reason that Smith, the author of the text, Professor Janice Smith, worries about solvent is because she is a classically trained synthetic organic chemist. And if you look at the text, you can see her talk about really elaborate molecules that she and others that she's worked with have synthesized. And if your job is to go in the lab and make stuff, you do have to worry about what solvent you're going to use and whether or not your solvent has really has a bond between hydrogen and an electronegative atom actually can matter. For example, when you get to 352, you're going to see a reaction. I'm oversimplifying it, but you're going to see a reaction where a carbon nucleophile, this would be something that was both a good nucleophile and an exceedingly good base, attacks the LUMO of a carbonyl. And it does a reaction where it attacks the carbon and you break the pi bond. That's not important until 352, but this is such a good base that you do not want a protic solvent. Tell me, what would happen if I used water as a solvent? Yeah, it's gonna rip the hydrogen off. It's going to be an acid-base reaction. pKa of water is 16. In contrast, the pKa of the conjugate acid of your nucleophile there, that has a pKa of 50. So an exceptionally bad idea to use a protic solvent in that case. And that should eventually get to be just common sense for you, not worth memorizing, but an important practical issue. If you did that, you might start a fire because of the vigorous nature of the reaction and the heat released. In any case, you would be you would be turning an expensive good nucleophile into a very cheap gas, butane, which could then light on fire. So as I said, from a practical point of view, this is important. The other reason it becomes important is just that for these reactions, the SN2 reaction and the E2 reaction, notice that we're using charged molecules. We have a charged nucleophile, and after the fact, we have a charged leaving group. And so and the same thing for the E2 reaction, we have a charged base and a charged leaving group. So going back to intermolecular interactions like we did in chapter 3, from a practical standpoint, if you want your starting material and products and leaving groups and nucleophiles to be soluble for SN2 and E2 reactions, probably it's a bad idea to go with something like hexanes that can't interact with charges other than by weak van der Waals interactions, right? So instead, for these reactions, you might want solvents that can interact with charges. So for a lot of SN2 reactions, we use polar to solubilize charges, but aprotic solvents, and we go with aprotic to avoid undesired protonation events. I don't know if that's... So examples of solvents that we use often in SN2 reactions might include acetone. This is a polar aprotic solvent. There's no electronegative, there's no bond between hydrogen and electronegative atom. Another example looks sort of like acetone, but is pretty different. This is dimethyl sulfoxide, or DMSO. Another is called, and you don't need to memorize these, dimethyl formamide. Also lacks bonds between hydrogen and an electronegative atom, but all of these have dipoles. All of these have carbon bonded to an electronegative atom. So these are examples of polar aprotic solvents that you might want to use in an SN2 reaction. Yeah? Okay. Examples of polar protic solvents would be water, methanol, ethanol, and there might be others that you can think of. Those are the ones that immediately come to mind. Smith talks about how the identity of the solvent, whether it's polar protic or polar aprotic, can change how nucleophilic certain atoms are. However, never in the text do we go on to say, oh, well, if I use a polar aprotic solvent here versus a polar protic solvent here, the consequence of the reaction changes and it's SN1 instead of SN2. There's an area of OChem that looks at that, but we're going to ignore it. And because it's not a real decision tree point, it's good for you to know what polar protic versus aprotic solvents are because of what you'll encounter in 352. But it's not important right now that you worry about why polar protic solvents and polar aprotic solvents have different orders of nucleophilicity in them. You'll read in the text that, oh, if I'm in a polar protic solvent, iodide is a better nucleophile than F- fluoride. But if I'm in an aprotic solvent, fluoride is a better nucleophile. We're not going to worry about that. So I'm not going to ask you questions about which nucleophile is better in polar solvent, polar protic versus polar aprotic. And I'm also not going to ask you which solvent is polar protic versus polar aprotic, because I have much harder questions than that to ask you, and I'd rather you not memorize stuff that won't turn out to be useful in the short term. Yeah?
Just to clarify, what degree do you want us to understand these then to be tested on? Just very basic, like you said.
What are you worried about?
I just don't want to understudy it if I could go there. Shoot, that would show
Okay, if you're aware of the distinction, and if you can recognize polar protic solvent from polar aprotic solvent, I think that's good enough skills at this point. However, I'm not going to ask you on the test, is this a polar aprotic solvent or a polar protic solvent? Because that's a memorized type question, plus, flip a coin. I do ask you flip a coin questions like with E and Z and R and S, but at least those are important skills to develop. This is not that important at this stage. Others? So I'm sorry for spending like 10 minutes talking about it. Golly. Okay, we've talked about stereochemical consequences of the E2 reaction. I want to now deal with regiochemical consequences. And what we mean by this, returning to our previous example that we can't seem to get away from, in our alkyl halide here, where we looked in detail at what the LUMO was, we saw that there were beta protons on different carbons. Okay, and that's an issue of if we remove one, we're going to get one constitutional or regioisomer. Some of you learned the term constitutional isomer in Gen Chem, and then you promptly forgot it. Constitutional or regioisomers, what does that mean? That means different connectivity, different bonds. Same atoms, same molecular weight, same molecular formula, different connectivity, different bonds. So, if we're going to call HA, HB, and HC. Beta proton C is on a different beta carbon than our protons A and B. We already showed that if you remove proton A versus proton B, you get the cis and trans isomers, right? And that was an issue of stereochemistry. However, if you remove proton C, what's the product you're going to get? Where should my double bond be? Yeah, right there. Okay, and if that's challenging, let's draw the reaction like this. Base removes the proton, leaving group, form a pi bond, leaving group leaves. Yeah. The relationship between the molecule here and the molecules here, these two are, these groups are regioisomers. They differ in the connectivity, in the location of carbon-hydrogen bonds, and in the location of the double bond. All right, these two are diastereomers. Okay, so by the way, why didn't I worry for proton C? There's two other protons on that carbon. Why didn't I worry about which one was anti to the leaving group? Does it matter for that carbon? Why not? It's not a stereo center, and the methyl group can rotate, and no matter which way you rotate, you're going to end up with two hydrogens there. So there's no stereochemical issues there to worry about. So I didn't worry about it. Okay, so you've got two different regioisomeric outcomes. Now we have to decide which is the major one. And again, as we've discussed during the first hour, the Zaitsev rule tells you the most stable alkene is the major product, and the most stable alkene is the most substituted one. And then when there are issues of cis or trans, that can figure in as well. So we would say that this regioisomer here on the right is a minor product, and these diastereomers are the major product, and then within that you would say probably the trans dominates over the cis. Okay? Now, the regiochemical consequences of the E2 reaction are going to be identical for the E1 reaction. So we don't need to learn anything new there, other than to say that if we take this same starting material, I'm not going to worry about which stereoisomer it is. Fine, we can worry about it. And if we use methanol as our nucleophile, that's a weak nucleophile and a weak base, whereas our starting material is a secondary alkyl halide. So nothing happens until the leaving group leaves, and you get a secondary carbocation. The SN1 pathway has the methanol coming in and attacking the carbocation from above or below. I'm skipping to the very end because there's a subsequent deprotonation of an intermediate we have to deal with. But we now have a carbocation, and methanol is now a good enough base to remove any of the beta protons. And so we can get, again, all three of these products, stereoisomers and regioisomers. And we can probably say that these diastereomers are the major product, and this regioisomer is the minor product. And then within those diastereomers, we could, if push comes to shove, we would say the trans dominates over the cis. So exactly the same issues for E1 as E2 in terms of regioisomers. Now somebody asked, this deal with the proton being anti to the leaving group, does it matter for E1 once the leaving group is gone? And the answer is no. So we're going to say there are no stereochemical issues to keep track of for the E1 reaction. The reason for this is we have to go back and look at what the LUMO looked like for, a little bit further, go back and look at what the LUMO looked like for a carbocation. And shoot. And I want to compare that to the LUMO for the alkyl halide. Okay, and I'm not sure. Yeah. So for the alkyl halide, we saw that there's no LUMO on the other beta proton. And that's because the sigma star has bias and directionality. The the part of the sigma star that's most important is projected back behind the CBr bond. In contrast, the LUMO or the p orbital in the carbocation is evenly distributed on one side versus the other, and so these protons on the bottom can start to overlap with that part of the p orbital. So LUMO actually in the carbocation is on mostly on this one that's lined up, but also on these other ones. And then notice that in the carbocation, I can rotate around that bond, so any one of those protons can be anti to the leaving group. But what I'm saying is there's no stereochemical issues at all for the carbocation. The molecule isn't chiral anymore, and differences between protons go away. And so we don't have to worry about stereochemical issues for the E1 reaction. Yeah?
So the first example makes sense why it's not, why it doesn't matter when there's 3 hydrogens. But the example on the right where both sides of...
Okay. I see where you're coming from.
It's different.
I see where you're coming from. Different, sorry. Yep, I get it. So let me just redraw this molecule so it's a similar thing. So we would see if you calculated the LUMO for this molecule, I'm going to draw what you would see. Don't worry about the phase relationships, but what you would see is there's LUMO on both of those.
Okay,
so,
if there's only one hydrogen?
Sorry?
And what if there's only one hydrogen?
If there's only one hydrogen, okay.
So you're saying there's LUMO on both of those?
So what I'm telling you is, in this direct comparison, the same molecule, but in the sort of carbocationic intermediate of E1 versus the E2, in E2, only one proton is reactive. In E1, because of the p orbital being evenly distributed on both sides, both protons are reactive. Now, you wanted to say, well, okay, let's make it worse.
So would there be 2 possible products?
From here?
From E1?
Yes.
Okay.
Right, from E2, if we did the E2 reaction, we're going to get I think this is maybe getting more convoluted than it needs to be. I'm trying to reason through this, and I think your question about what if there was only one beta proton over here, if there was only one beta proton, there would only be one product.
I was only asking about E1.
Okay. If there was only one beta proton, I could still spin around this bond to line up this proton with the p orbital, and so there's no stereochemical issues. Yeah. So yeah, in an E1, E2 reaction, you have to worry about is your beta proton anti to the leaving group. For the E1 reaction, you don't. That's the punchline, and it has to do with the MO picture. I apologize for how convoluted that explanation was. The real good example to look at, if you wanted to reason through that on your own, would be to look at what happens for this starting material. It would be good to convince yourself that if you did this stereoisomer in an E2 reaction with, say, a sterically hindered base, you would only get the following product. Whereas if you took the same starting material but you used conditions that would favor an SN1E1 reaction. Let's use water as our solvent. What you're going to see in terms of products are going to be both stereoisomers that you would get from the SN1 reaction, because the nucleophile can come in from both sides. These are SN1 products. And then for your E1 products, you're going to get both the the E and the Z isomers. And the reason is that once the leaving group leaves, you have an empty p orbital, and there are multiple ways for the single beta proton to be lined up with the empty p orbital. So that may be worth going through and convincing yourself that that's true. Ultimately, this would be, you would be looking at some kind of carbocation like this, and you would reflect that, hey, if I rotate around this bond, I can bring this HA to be lined up with the p orbital anyway, so actually it doesn't matter which side it's on. Okay, so with that in mind, we're ready to sort of forge ahead into painful examples and practice. And I encourage you to do as much or as many painful examples and practice as you possibly can. Because only by, this is the kind of thing that you can't just memorize and hope for the best. Go ahead.
Sorry, so with the E2 reactions, if there's like more than one beta per proton, do you still only really get one result, like depending on the configuration you started?
Right, so the reason we only got one product from this is because there was only one beta proton. Our other example where we introduced this issue of stereochemistry, we have two different beta protons here, and they can both be anti with the leaving group depending on if we rotate around this bond, so that's why we get both of those products. Yep. All right. So getting through all of this is like learning to play a musical instrument. You can't just learn the names of the notes, and then you can't just learn that, I don't know, the spaces on the treble clef spell face, F-A-C-E, whereas the lines are like every good bird does fly or something like that. You can't just memorize that and then sit down at the piano and hope to be able to play at tempo while you read the music. You know all the rules, you've memorized it, and still you can't play it, right? So it requires muscle memory and practice and performance. This is more about what you can do than what you know. So you can't just memorize the table, you actually have to do examples. And there should be plenty of them in the study guide and the practice exam. Let's start. I'm going to just give you a few here. And yep. So here is BR. Oh, this is a delightful example. I don't know why I've made it this terrible. And then let's use CN minus as our nucleophile. This might be written KCN, but that's just CN minus with its counter ion. They might write a solvent below the arrow. CN minus is on our list of good nucleophiles. Its conjugate acid HCN has a pKa of 9. So this is a good nucleophile, though its lower pKa would place it as a weak base. Our alkyl halide is on a tertiary carbon. That is a carbon that's bonded to 3 other carbons. So that would tell us there is no SN2. Our good nucleophile but weak base, good nucleophiles would prefer SN2, but that's not an option due to the alkyl halide structure. And CN minus is a weak base, so that will also rule out for us E2. All that's left then is SN1 and E1, which is okay for a tertiary alkyl halide. So from this point, it's good. You can try to predict the products going forward. You can also draw the mechanism, and that can sometimes help you with the stereochemical issues, if there are any. Notice that as I draw this carbocation, my drawing indicates that the carbon that used to have the leaving group is now trigonal planar, sp2 hybridized, and I know that the p orbital that's on that carbon would be evenly distributed on top and on the bottom. I also have to fill in this other methyl group. Okay. Now, if I have a carbocation, I need to think of both SN1 and E1 products. So for the SN1 product, then I can have CN minus attack the carbocation, but now because I know that that carbon is sp2 hybridized trigonal planar, I know that the CN minus can attack from either side. So I'm going to draw as products both of these, one where CN comes in from above, one where it comes up from below. What is the relationship in stereochemistry between those two products? Are they enantiomers? They're diastereomers. Why? Because you got this other stereocenter that's not participating in the reaction, right? And that doesn't change. Therefore, these two are diastereomers. Now, diastereomers don't have to form in 50-50 ratios. It could be that this methyl group here pointing up sort of blocks partially the top face, making approach from the top side a little less favorable than approach from the bottom side. So you wouldn't be surprised if you went into the lab and you found that you had a slight excess of one diastereomer over the other. It's only when you form enantiomers that they have to form in a 50-50 ratio. That's a subtle point, not a major one, and I'm not going to ask you which one dominates, but it would be incorrect to draw the product as follows. It would be incorrect to draw the product like this with the plus or minus, because that indicates that your products are enantiomers and they're not. It would also be incorrect to draw the product like this, because that indicates all possible diastereomers, which is not true. You only get these diastereomers, none where the methyl group is down. It would be okay to draw your product like this, because the stereocenter's there, and then you communicate with just the regular lines that you've got both configurations here. Okay, so subtle issue, not a major one, but it's something to be aware of. Now, how about the E1 products? For this, we need to go in and identify the beta protons, protons that are beta to now the positive charge. So I've got one here. I've got two here. And I have one here. So if I do the E1 reaction to remove the blue beta proton, my product looks like this. I meant to draw that in blue. Oh well. In contrast, if I remove the orange beta proton, my product would look like this. And if I removed the purple beta proton, my product would look like this. Okay, 3 different E1 products. For this question, you would simply, a correct answer to this question would simply draw all of the products. The way this might be formatted in multiple choice is I would show you multiple possible products, and then you would have to choose. It could either be one of those terrible ones where fill in all of the right answers and none of the wrong answers, or it might be 1, 2, 3, 5, 7, 9, and 12 are correct products, and the others are not. In any case, I would not ask you to tell me whether SN1 products dominated over E1 products. Though, if I asked you among the E1 products, which is the major one, which would you pick? The black one, which should have been blue. How about them apples, huh? Change the color. Okay, good. There's a couple others that I would like to do, and maybe will next time, though I want to demonstrate something that can complicate things. Grateful for that, aren't you? So, if you look at this alkyl halide, you would be tempted to call it a primary alkyl halide. And it definitely is, but that's not the best descriptor. And the reason for that is that for a regular primary alkyl halide, if it left, you would have a localized primary carbocation. But in contrast, if this group left, is that the same as a localized primary carbocation? Objection, Your Honor, leading the witness. Why would I ask it if the answer was yes, it's the same? It's not. The positive charge is adjacent to a pi bond. So by resonance, I can delocalize that positive charge. So now that is not a primary carbocation. Rather, it is a resonance stabilized carbocation. A resonance stabilized carbocation, which means it is an okay intermediate. And SN1/E1 are allowed. Okay, so we said in our table at the very beginning, primary alkyl halides, no SN1 and E1. Maybe you want to put an asterisk on that and just say watch out for resonance, the possibility for resonance stabilized carbocations. If that can occur, then SN1 and E1 are a possibility. Resonance has other consequences. So it might be, well, put it in this particular example, why not? So if we were to have this alkyl halide react with something that is a poor nucleophile and a poor base, what would the products be? Well, we would need to draw these carbocations as intermediates, and then we would need to draw the possible SN1 and or E1 products for each resonance structure. I laugh. So do that with this one and see what you come up with. And then I will put the answer in the notes. That is basically it for chapters 7 and 8. Anything else we might do would just be practice. And so I hope I've sort of shown you how to go about thinking about these things systematically. We will try a couple of example problems next time, but we'll move on to the next chapter. You're going to have to spend the hours needed to do the practice and get used to this stuff. So we'll end there and send you off to work.